So, welcome back to this new session of uh, CFD. So, in the last session, we had looked on solver technology, that is explicit and implicit solvers, steady solvers, and transient solvers. We had also looked upon grids, that's your velocity pressure, pressure velocity coupling, and how you solve it. So, then you had also checked on collocated, staggered, and collocated with rejoint interpolation. So now we'll be jumping on linear equation solvers. So now we'll be looking at the mathematical models, right? So till now we were focused on physical models, but now we'll be jumping on to mathematical models. And so yeah, let's start. So we had talked about coupled solvers, right? Coupled solvers. Again, please don't mind my handwriting, but yeah, hopefully the explanation should compensate it. Compensate it. Huh. So yeah, so in coupled servers, I told you solve it using matrix, right? So what happens is that you have um, matrices with like a million terms, right? So the normal matrices that we do usually just mostly comes up to like 8 to 10 degree, right? Or the order of 8 to 10. But in a CFD simulation, the backend uh, maths that's getting solved, you'll have matrices with around lakhs and lakhs and millions of terms, right? So that is why we'll be needing some solvers, that's those linear equation solvers. So a general linear equation is Ax is equals to b, right? So that is what we'll be solving. So for this you have many methods, and let's go on with each method one by one. So the first one being TDMA, right? So TDMA is diagonal matrix algorithm. Matrix algorithm, right? So suppose this is applicable only for certain matrices. So suppose the matrix is like B1, C1, 0, 0, A2, B2, C2, 0. Then you have A3, B3, C3. Then you have A4, B4, let's say B3, right? And the rest of it is 0, 0, 0, 0, 0, 0, 0, 0. Okay, fine. Uh, okay, I'm sorry, this is 0 doesn't exist. So here what do you see? So you see this tri-diagonal matrix. So you have three diagonals, right? This is one, this is second, and this is third. So it's like all A's together in diagonal, all B's together in a diagonal, and all C's together in a diagonal. So when you have such matrices, you can solve equations faster. So that's why it's called the tri-diagonal matrix algorithm. So you try to convert the matrix into this form using some conditioning, preconditioning, and then you try to solve the equation. So this can be solved directly, solved directly, and this is one of the most basic ones, which honestly at this time is not much used. So only 1D can be solved, one dimensional matrix can be solved, and most of it that we encounter now is 3D or more than 3 dimensional. So that's why cannot be solved. So that's why we don't use this method anymore much. I mean, it's still a very fast and convenient way. So from now we'll be going on to the uh, more useful ones. So the first one being, so if you have done numerical methods in your engineering, you'll be knowing. So the first the second method, this is a Jacoby method. So here what you do, so suppose I have an equation, let's say 10x plus y is equal to 11, and another equation x plus 10, oh my god, 10y is equals to 11, right? Now I'll, from this first equation I can write it as x is equals to 11 minus y by 10, correct? Then y is equals to, from this equation I can write y is equals to 11 minus x by 10. So yeah, this is, so from each equation you separate out one variable, and now what you do is you start guessing values, the initial values. Okay, so you guess, suppose the value of x and y to be 0 in the first one, so you assume y to be 0 initially, then you find x, then you assume x to be 0, and then you get a value of y. So and then you keep iterating it for many terms, so keep iterating. So what happens is, okay, now you have taken x is 0, y is 0. If you put it in these two, of course it's not going to get satisfied, because 0 plus 0 is going to be 0, 0 plus 0 is going to be 0. So of course it's wrong, but now you get a region to start with. So once you start with this, the values get updated until um, you reach this state, right? Both of them are satisfied. So first guess was 1, then you have a 0, then you have a correction, it becomes, suppose, I mean, you find out error, and using the error you update your guesses, and just keep going on, right? So that was your first method, that is, sorry, the second method, that was Jacoby. Now others are kind of improvements on the Jacoby system. So you have the Gauss-Seidel, one of the most used ones. So Gauss-Seidel method. So what does it do here? So it's the same thing as we did in Jacoby. So assume like 11x plus 2y minus z is equals to 12, and 12x plus y minus z, sorry, plus z is equals to 23. Okay, and then you have one more, x plus y plus z is equals to 16. Okay, I'm just taking this equations. I mean, I don't even know if it has a solution, but yeah, I'll just take them. So from this you can take, I mean, you can make out an equation. So you can write x is equals to 12 plus z minus 2y divided by 11. You can write y as 23 minus z uh, minus 12x divided by 1, and you can write z as 16 minus x minus y, right? Okay, so this much you understood as you had done in Jacoby. Now here, what we used to do is used to assume values, right? So now you have assumed a value, suppose y is equals to 0, and I mean, you take the best guess. It's not necessary that you take 0. You take the best guess, then you have put it here. Now you get a value of x, right? Now this x, so I'll call it xg now. Suppose you have found xg. Now you put this I mean, this value of x into this. So you keep updating it continuously, right? This is exactly what Gauss-Seidel does. So now you found a value of y, okay, using this updated value of x that you got from here. Now with this, you put the value of, so yg, so this new value you will substitute over here. So you have new value of x and new value of y, you substitute both, and then you find the value of z. So this is what happens. So, and then you check if it satisfies, and then you keep updating the values. So this is your Gauss-Seidel method, where you continuously update the value of x, y, z, right, in order to find the next values of x, y, z. So as simple as that. So this is a commonly used method now in CFD. Then, so you keep doing all these, you keep iterating it until your values converge, right? So the mode or the criteria that you choose your um, model or solver or method is based on how fast you can achieve these achieve convergence, or how fast your residuals can be decreased, right? Or it can limit of the residue tends to 0. As long as that rate is fast, you will choose that method, right? Because of course you are spending less computational time on that, so you have to spend less resource on those methods, right? So yeah, so moving on. Okay, why did I erase that? My bad. But so moving on to the next method, that is your SOR, so successive over relaxation. So assume like in the previous example, you had x had some equation. Let's say I'll just tell 12 minus z plus 11y by 2. Okay, y had some, again something, let's say 12x plus z minus 2 is by 1, and z was like, I don't know, 16 minus x minus y, right? So in Gauss-Seidel you kept updating, so this xg, then you put xg over here, then you get yg, then you put xg and yg and find zg, zg, sorry, huh? So I just uh, use them as, call them as Gaussian variables, so the Gaussian values. So what successive over relaxation does is that it is same like Gauss-Seidel, but your new value, that is xg, when you're finding the x new, you add a relaxation term, that is you're accounting for any errors, you're trying to minimize the residuals. And how do you do that? So your x new, the xg new is equals to your x old, okay, plus the relaxation term times your x g, the Gauss-Seidel one, minus x old, right? So what does this mean? So suppose I had taken y is equals to 0 initially. I got some y and z, I take some initial value. I got some value, say, let's say I took y as 0 and z as 0 initially, so I got x g is equals to 6. Okay, now so this gs is xg itself. Now the old value of x was 0. I assumed initially that x, y, z equals to 0. So now here what you do is you do 0 plus you do 0 plus w. So w is a term, and the relaxation term is like just a constant that is used in order to compensate for the errors and the residuals. So it is generally greater than 1. It's just something that you have to remember. So you put that, so let's say around 0.7 or 0.67 generally. So that now the Gauss-Seidel, that is 6 minus old 0. So 0.7 times of 6, that is 4.2, will be my x new. And this is again continuous updation. So when you put yg, now here you will put your xg new, right? So that is what the successive over relaxation is. It's just technically Gauss-Seidel method, but with a relaxation term that you are doing to reduce error and residual, right? So that is the whole idea of the SOR, the successive over relaxation method. Now, since we have done these three, let's now shift to another method. So now, right now we were focusing on finding values of the variables, right, x, y, z. Now the next method is different. So this is called the which was this 1, 2, 3, 4, 5. So this is called the Kirillov series. Kirillov solvers. So what does these do? They don't solve for any variable as such. What they do is they keep improving residuals. So by improving residuals, I don't mean increasing it. So you decrease the residuals, right? So suppose it's a graph of the value divided by time. You try to converge it as fast as possible. So the residual decreases, right? So as the solution converges to the accurate or the real solution, your residuals start decreasing, and that is what the Kirillov series does. So your residual is technically your b minus ax. So as I said, we are solving ax equals to b, right? So if I take the other side, b minus ax, whatever is remaining here, that is what is my residual, that is r. So I am just calculating r, and the goal is to tend r towards 0. This is the whole point of your Kirillov series. Okay, so this is now used in modern CFD. You just try to reduce residuals rather than finding every variable value, right? You do calculate the values, but you don't give much importance to it. You just try to reduce the residuals. So now moving on to GMRES, the next method, that is 6. So that is GMRES, or generalized minimum residual, minimum residual. So here what happens is just a tag along on the Kirloff series solver. Sorry. So in Kirloff solvers, once you have solved the entire all equations, you try to like after all iterations you reduce the residual, right? So what GMRES does is at each iteration, at each iteration you reduce you try to reduce the residuals. Now how is this helpful? Now you are way more accurate and fast. So accurate and stable. So because you're trying to remove the errors and residuals within each step or each iteration, right? So yeah, and this is mostly used for your compressible flows or compressible CFD, because again, as I told, transient and compressible CFD, usually if you go with the segregated or normal methods, you will just end up nowhere because it will take a lot of time, because there are a lot of equations to solve in compressible flows. So that's why you use coupled in the first place. But again, when you are calculating all this, that's why you use such methods where you can minimize computational time as uh, short as possible. So yeah, so this is your GMRES. Then you have the next. So these are just build upons. So you don't need to know anything in detail, just know that they exist and what each of them does, like a general overview. Don't need to know the backstory of it. So you have by CG stab. So the by CG stab is just by conjugate gradient stabilizer. Now what does this do? So here it's nothing that you have to know in the backend. It's almost the same as the previous ones, except that it consumes less memory, right? Less memory, and it's faster. So these are just built upon on the Kirloff series. You have GMRES, which does iteration at each of the step, and here you have modified equations, which um, make it take less memory and less storage, and it's faster to solve, right? So that's all you need to know. So this is like another kinds of solvers. So now next are important ones. So the seventh one is multigrid. So this is kind of important to understand what multigrid does. So when you're finding errors across a mesh, right? So there's a mesh, and suppose it's like very fine. Okay, suppose the meshes are very fine. So now you have to find error across each mesh, right? So the more fine the meshes are, the more mesh elements you have, right? So more fine mesh means you have more mesh elements, and therefore that means more computational time, computational this, right? to find to find errors. So you find error across each uh, what do you call each mesh, right? Each mesh element or each control volume is what you find errors on, right? Because you enforce each of this equation in each of the control volume, and then each control volume has its own errors, which are then aggregated by the solvers, right? You try to convert solution in all of them, right? So here what is the solution that you can go to? So if you think logically, your problem is that the meshes are fine, that's why you have a lot of mesh elements to find errors through. So what if we temporarily create a coarser mesh, right? So this I convert it into larger mesh, something like this, right? So in this what happens, now I can just find errors at these big meshes or these big control volumes, right? And I can take this as an approximation. Might not be the exact errors, but I can take that as an approximation and almost close to the real ones. So that's what multigrid does, is that it converts this finer mesh into coarser mesh, then it calculates the errors, corrects them, so corrects error, and then converts it back into fine mesh. Okay, if that's understood. So if you're doing singularly each of these fine mesh, it would take a ton amount of time, a lot of time to compute the error for each and then have a correction for each of them. So what multigrid does is it converts into cores. So even if there's like, okay, let's say this big mesh has like 8 smaller meshes within it, right? So right? So what happens is for the multigrid solver calculates the error for this whole big mesh element, and then it distributes its errors across the fine elements. Now it was easier to calculate for these the big mesh elements, right? So now once it's distributed, it is almost close to what you would get in just a finer one, but you have calculated it like faster, way faster than you would do it in a finer mesh. And so correction is also easier now. So since you have calculated all the errors, now you can correct it and then use uh, convert convert the coarse mesh back to fine mesh, right? So if that makes sense, what you have done is you had a coarse mesh. It's tougher to find errors in this because you have to do tons of calculation for each of them then, because you are enforcing that all these equations in each control volume. So what you do, you convert into coarse, um, then you calculate errors in these coarse meshes, you correct them and then convert back into fine mesh, right? And these errors are distributed, and corrections, these are distributed into the smaller ones that exist inside um, the coarse ones, right? So this is multigrid. So now there was one problem with multigrid. Again, now converting it into um, bigger mesh would take time, right? Physically, if you're doing so, but also the good thing about this multigrid was that you would it reduced the convergence time dramatically, like drastically. So the engineers couldn't give up on this idea. So what they did is just think logically. Instead of directly physically modeling these meshes, what if you just use the maths behind it? So now you have this new method. It's called AMG, that is uh, algebraic 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 multigrid. So whatever multigrid did physically, this would just do it mathematically. So of course, multigrid, everything runs around maths, right? So you converted all these coarser mesh into finer mesh into coarser mesh, and found the errors and corrected them using maths itself. So geometrically, you are converting them into a coarser mesh using the equations, right? The geometrical equations. So in this, AMG directly uses those equations. So you are not physically creating um, you don't you don't physically create a coarser mesh, just mathematically mathematically and it's lagging, yeah, mathematically model it, right? Now what has happened with this, you don't have to physically create a mesh, right? So now your computational time has gone down. So your computational time reduces time reduces insanely, like drastically, right? So that is why AMG was like a revolution in CFD. So you are now algebraically uh, trying to form the meshes, the coarser ones, multigrid coarser meshes. Then you're calculating error as you were doing the multigrid system. Then correct those errors. Then convert it back to the finer mesh. Again, it was already a finer. It was the mesh geometrically remained fine itself, but mathematically you converted it into um, your coarser mesh and found the errors through those mathematical equations, and then you distributed all the errors and distributed the corrections and just kick them back into the finer one. But but geometrically the whole surface still had the finer mesh, right? So this is how you saved a ton of time, and that's why this is highly fast, and it has the same convergence rate as multigrid, and that is why this is now almost used in all CFD uh, simulations. Now the next one that comes is just a small thing. It's called preconditioning. So preconditioning. So what is preconditioning? Well, this is just some matrix changes that you would do. So suppose your matrix was something like A is equals to, you have like 1 0 0 2 8 2 0 0 1 1 9 2 8 0 0 something 0, right? So this is difficult to solve. Difficult to solve. So what preconditioning is that, so this is Ax equals to B, right? Ax equals to B. Now what if I multiply some matrix here, Ax is equals to m minus 1 B, such that this matrix value is simple down. That means now after multiplying it with m, another matrix m inverse, some matrix, you get some simple down version of like 1.28, 0. Some 1 and 0.1 and 0.928, and just an example. So it's, you can just like in ML you use an activation function, or you can use some scalar, standard scalar, like what you call standardization, right? That is exactly what we are doing here. You're trying to convert it into some small scale, or you're like scaling it down so that it is easily solvable, right? So that is what preconditioning is. So now we have just checked on what all methods are possible. So generally, what Fluent, something like ANSYS Fluent uses is your AMG, that is algebraic multigrid, plus it uses Gauss-Seidel smoothing. So it uses Gauss-Seidel to smoothen those uh, values. Then it uses Kirillov solver to reduce, this is to reduce your residuals, and plus preconditioning, right? So we have discussed all this, and this is what goes in the backend when you are running a mathematical model behind, right? So when you have ran a physical model, now when you have to find the values for all of them, you have to run a mathematical model, for which you use these. I mean, ANSYS Fluent uses this, and most of the modern CFD tools also use this as the backend. So yeah, this is how um, all these mathematical models were necessary to understand what's going on in the backend, and hope you have understood this part. So uh, next, what I would talk about would be your stability and convergence. So stability and convergence is an important. Okay, so stability and convergence. So let's talk about what they are and how they are important. So the next topic, stability and convergence. So stability and convergence are one of the most important topics in CFD, as I've been telling for all topics previously. But yeah, this is something that is required, because until your solution converges, usually in CFD, you don't uh, get the solution validated, because if your solution diverges, it means something is wrong with what you have done till now within the simulation, right? So what exactly are each of these terms? Let's see. So I'll just see if I can make this pen thicker. Okay, it's 5. Okay, so yeah, so what it can be divided into three three parts. So you have um, consistency, you have stability, and you have convergence. Now what does each of them mean? So we'll start off with consistency. So consistency means just ask yourself this question: that does the discretized discretized equation approach the original partial differential equation as as the mesh gets finer. So what it means is, so we had discretized partial differential equations, right? So we discretized them into simpler equations, right? Using the values of the function itself, as if you remember, we had used like Taylor series, or we had used forward, backward, and central difference methods. So this we converted into simpler values using the uh, values of the function itself to find the values of the partial differential equation. So what we check in consistency is that if both these give almost the same value, and as your mesh gets finer, you have to be more accurate. So as your mesh gets finer, does both of these um, give almost equal values? Okay, now if your mesh is coarse, it is bound to have some inaccuracies, right? So what we check is that as your mesh gets finer, do these two values um, come around the same line? And if they do, then so if they do come around the same line, then it is consistent, and if it is not, it's inconsistent, right? So discretized equation should behave closer to the original equation, and that is exactly what we require, because the whole point of discretization was to simplify it, and we didn't want to touch up with the accuracy of the PD, right? So it takes a lot of computation to solve a partial differential equation. So that's why we go on with discretization. So our end goal should be that both of them should at least give around the same accurate result, right? So that's why consistency is an important part. Then moving on to next, that is stability. So in stability, so stability, it's you ask yourself that if whether the error dies over time. So if you have an error, does the error die over time, right? So technically, in short, if your residuals become less, right, or approach to zero, that is what your stability means. So your sources of error, sources can be, we have discussed this earlier. So round off, like if I'm rounding off because of a constraint of storage, then that can be an error. So if it's like 5.23982, I just take 5.239, that is a round of error. Then your mesh inaccuracies, as I told, if you go for a coarser mesh, you have high inaccuracies right? So a finer mesh means you are more accurate, so that's why you have an error if you're going with a coarser mesh. Then you have discretization error. So this we had looked up in consistency. So your consistency looks upon this factor, that is discretization error. Then you have interpolation. So when you are interpolating any values, if you are getting any wrong values as such, then that is your uh, interpolation error. So yes, these are the sources of errors, and you check whether uh, these errors die over time. And if they do die over time, that means your solution is stable. And if they are not dying over time, there's a high chance that your solution is going to diverge and it's not correct, right? So now, what is convergence finally? What is convergence? Convergence. Okay, so convergence, it's just a mix of two. So your convergence C is equals to your consistency plus your stability, right? So the above two, whatever we saw, if you add or if you merge both of them, that is your consistency. Sorry, that is your convergence, right? So if we just talk about it, in general, you can just say that uh, does so the question you can ask yourself is, does the numerical solution approach the exact approach the exact solution, right? So this is more like something that you have to validate. So if you're that the system also validates that if your numerical solution that you have been using, so the uh, physics and the mathematical models, if they are good enough that the numerical values that they are providing is matching the exact solution, then it is a converging solution. Else, it is it doesn't converge. That means you the opposite of converge is diverge. So your solution will start diverging, right? So you usually in your answer fluent or something, so its solution with respect to time steps, you will see that the value converges like this. So and if it is not, it just goes like this, just diverges out of the plane, right? So that is something that we don't want. So we always want our solutions to converge, but a convergent solution doesn't always mean that um, it is always the correct one. So your sometimes your solution can converge, but it is not necessary that uh, your the value that you have obtained is correct, right? So converging is just saying that you are error free, but it error free from the values, but it doesn't mean that that exactly is the value for this kind of problem, right? So it's like if I get point 0.1, point 0.1, point 0.1 as my answer. So it says that now my answer has come into 1 point. So this is my convergence, right? This is not necessary to be. So this point 0.1 may not be the correct value of the parameter that I am looking for, right? But it is converging in the sense that the errors are reducing and it is stabilizing to one value, that is point 0.1. So that's what I mean. So if it's convergent, it's not necessary that it has to be correct value. So your sometimes you might have done something wrong in your model, like some you might have given a wrong equation. So the solution might converge, but uh, your answer is wrong for that particular problem, right? So yeah, that's what I was saying. So if you have given boundary condition, that's more like an human error that you have given something wrong as an input. That's why you're getting a wrong output. So the system usually solves according to whatever boundary conditions and uh, stuff you give. So that is something you have to look for. So yeah, just keep in mind if it's converging, don't assume that the solution is the correct one. Okay. So please always check in uh, 10 times before you run a simulation, right? So yeah. So now let's jump into causes of divergence. So this is just to give some insights. So causes of divergence. So what all can cause divergence? Well, number one, it can be bad meshing, right? If you are given a very coarse mesh, don't expect if it's coarser mesh, then it's worse because you are not accurately resolving each of the geometry. And again, you have metrics. So if you have high skewness, so if you remember what I told, skewness means how distorted it is. So high skewness means highly distorted. And if you have poor orthogonality, so orthogonality, as I said, was like the alignment between the lines joining the center to center of the mesh element and the face and the line that goes outward to the face to the direction which the face is facing, right? So it can be poor orthogonality. And so orthogonality, if you have 0 it is bad, and if you have 1 it is good. In skewness, if you have 1 as skewness it's bad, if you have 0 it is good. So it's like opposite of each other, right? So yeah. And there's also possibility that your boundary layers aren't resolved properly resolved properly. And what do I mean by this? So I told you at the boundaries you need very fine mesh in order to capture everything like shocks and etc. Right? So if your suppose if your y plus is too high, it means that your mesh is coarse around the boundary. So this is something that you avoid, right? Especially if you're doing some transient and turbulent analysis, then should avoid um huge y plus value. So yeah, next point is, or the next way that you can go wrong is by wrong boundary conditions. So boundary conditions are just conditions or constraints that you put at the boundary conditions. So yeah, so my bad on that. So yeah, if you have like some, I don't know, if you take an airfoil, I mean, if you take a propeller here, right? So this is a propeller, then I make a boolean outside this, and then I simulate the flow inside, right? So the boundary conditions here, this would be the inlet, this would be the outlet, this is the propeller, right? So and these are the walls. So what I would do is just inlet I can put I'll put velocity, then at walls I'll put no slip, and this for like a standard simulation, no slip, and outlet I'll put some pressure outlet. So pressure outlet. So yeah, this is the boundary conditions that you usually put. So you are just technically giving the constraints and parameter values at the boundaries so that the flow can be simulated within that domain or within that region, right? So now if you give a wrong boundary conditions, of course your whole simulation goes wrong. The number three uh, is huge under relaxation. Huge under relaxations. This is just related to some numeric stabilities. So yeah, so I mean there you had seen with respect to values like x. So your x is equals x new is equals to x old plus w times of xg minus x old, right? This was the under relaxation term for the variables. Now here you can also do it in terms of like the parameter terms. So like p new is equals to p old plus alpha times p uh, um, the p calculated minus p old, right? So you have an old value, the old values and the calculated value, and if you put this with alpha, your alpha is your under relaxation term, relaxation. So if your under relaxation is too huge, then you get a very distorted value of p. So that's why you always try to tend to keep less over relaxations. Now next cause could be poor initialization. Poor initialization. So you always initialize the value for the parameters, right? So that you can start. So that is exactly where you're starting your guesses from, so that you can run the simple equations. I mean the simple solvers, simple or depends whichever solvers you are going with. So you have to initialize values, right? That is how you're starting, because you don't know the exact values and you're using discretization. So you have to have an initialization first. So you will have an initial field, right? Within which, that's a domain within which you will start your guesses, and then this expands as you reach closer to the accurate solution, right? So the fifth one is what I discussed earlier before in that session, is that the first iteration first iteration with 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 second order uh, up in concept. So you always do, as I said, FOU first, then once converge, you go with SOU, right? So this is just a standard approach that you use. Nothing much to think about. I had explained the reason back then. You can just review that. Then sixth one, a large time step. So large time step. So in large time step, what happens is your CFL becomes large. So your CFL becomes huge, and that is something that you don't need. I mean that you shouldn't have, because if CFL increases, that means your simulation is mostly gonna diverge. So how is time step related to this? So it's like your u delta t divided by del x, right? So if this increases, your CFL is gonna increase, and if you're skipping a lot, you're missing on details, and so you will end up at a situation where your solution will diverge. So that is something you don't need. And next is simple. So it's just wrong model. Wrong model, you might have chosen the wrong species model or turbulent model, or I don't know what a turbulent species is energy models. So that's again something that is up to you, and thus these are the cases on or reasons how you could go wrong. So I'll just reiterate it. So one is that you have a bad mesh, then you have a wrong boundary conditions, then huge under relaxation, poor initialization, then that you go first with second order. You shouldn't. You should first go first order, then converge it, and then go second order. Then it's a large time step. Then you that's a small another reason that you can have reverse flow. So that is something we won't discuss now. So that usually happens at pressure outlets, and then you have wrong turbulence or any model, right? So particularly when you have a separated flow, you should be very uh, conserved about your or very uh, focused on the uh, model you are using, right? And just to remember again, your true convergence requires residual and physical convergence. So just residual convergence doesn't mean it's physically converged, um, or it doesn't mean it's truly converged. So yeah, this I had discussed before, right? So if it's just the residuals that have converged, that means your solution is converging to one answer. It doesn't mean that that answer is correct. So that is your physical convergence. So yeah, it can be that the thrust, suppose, is converging to 1700 Newton, but it's not necessary that the answer is 1700 Newton, right? The actual thrust that I get through, suppose, simulating a nozzle. So that is all about it. So now we'll jump on to how the workflow is in Fluent. So this would be the final thing I'll be covering before jumping into um, turbulence model that we'll be checking next session. So yeah, we'll check how Fluent workflow happens. So now coming to Fluent workflow, I'll just take ANSYS Fluent for now. I mean, you have multiple safety softwares, OpenFOAM, SU2, that is Stanford University 2 solvers, and ANSYS Fluent. ANSYS Fluent is one of the most used, so I'll just um, go with that. So the Fluent workflow, right? So how exactly everything happens now. So first you initialize value, initialize, okay. You get, so you use FOU, then you use second order SOU, you check residual, you check residuals. So okay, your FOU, then you converge first the first time, then you use SOU, then after SOU, then it converges again, right? The final convergence. Then you residuals, check residuals, then you check the physical convergence, check physical convergence, convergence. So now if I'm taking a I don't know, example of rocket motor simulation. So I'll check thrust, I'll check mass flow, I'll check the outlet Mach, etc. So I'll verify that physically, and then I'll do a grid independence study. Grid independence study, study, and then I get the final results. Final results. Okay, so what does grid independent study means? Okay, so this is just easy to understand. So you know that the more accurate your mesh is, your answers keep getting more accurate, right? So in it, the more finer your, okay, let's close this. yeah, the more finer your mesh is, so the more finer the mesh gets, uh, the more accurate results you get, you get, right? So now after a point, there'll be a point after which, even if you go more fine, like, so after a point fining the mesh, that is making the mesh finer, uh, making the fine tuning the mesh, or making, so you can either fine tune the mesh, I mean, in the sense that you can make the mesh finer. Making the mesh finer doesn't uh, doesn't change the accuracy of the solution more, right? Okay, by much margin, right? So let's say that for the value of thrust, okay, there was a value of thrust, and let's say that, uh, I'll just call it mesh. So first it was a coarse mesh 1x, right? So it gave me around 2500 Newton. Then I made it 10x medium mesh, so I got 2220 Newton. Now I start making to finer mesh, so 100x. So now I'm trying to get around the value, so 1780 Newton. Now I go 1000x, I'm getting 1760 Newton. Fine. Now I go, suppose, another x. Now I start getting 174, or, oh sorry, 1758 Newton. Then 1000, another finer mesh, I get 1759 Newton. So this is when, um, like, even after making the mesh more fine, you are getting around the same result. So the accuracy is not changed. So suppose the actual value is 175 uh, 58.6 Newton is the actual physical convergent value, right? So you can see that it is, I mean, the accuracy is not changing much even after making the mesh finer. So this is when you say it's grid independent, in the sense that even if you make the grids or mesh finer, it's not going to affect you uh, much more, right? It's not going to affect you. It's not going to affect the accuracy anymore. So that is what we call as the grid independence state, or the state after which even fine meshing doesn't help out in getting a more accurate result. So that is where you stop your simulation. That is that you can't go further to get a more accurate result, right? So that was everything about the Fluence workflow. And yeah, so now we have covered all mathematical models and solver technologies, and then your convergence and your stability, and yeah, reasons for your simulations to fail. We have covered all that. Now the only thing remaining is you have Riemann problem and turbulence modeling, and then you have advanced CFD. So this I'll be covering up in your next session. So if you have any doubts till then, so yeah, just let me know in the comments or DM me at Kashyap Binu on LinkedIn. So yeah, thank you.